So we saw that given a hyperspace, there is a canonical way of seeing the dual of the hyperspace isomorphic to be isomorphic to the hyperspace itself. The same thing will not be possible for norm vector spaces. However, now we are going to see how, if you take the dual of a norm vector space, then it could be big, but inside it, you can still see the initial norm vector space. So let's V be a norm vector space. And so we consider V star the dual. And as we said, this is a normed vector space. Okay, we also show that this is actually, it's complete. It's actually Banach. So it's a Banach space. Now what we are going to do now is we are going to do the dual of the dual. So the dual of the dual of V. This is called Bidual of V. And again, this is a Banach space because it's the dual of a norm space. Okay, the theorem that I want to present is the following. There exists a canonical linear isometric embedding of V into V star and is the following. Given X in V, we send this X into the map, let's call it Phi-X in V star, which is the evaluation where Phi-X is the evaluation at X, which means that for any element lambda in the dual of X, Phi-X of lambda is lambda calculated in X by definition. Okay, so this, and what I'm saying is that this map is linear from V into the Bidual. Might not be surjective, but it is norm preserving. So this is what isometric embedding means. Proof. So everything will be quite easy to check, except the fact that the norm is not going to be smaller than 1. For that, we will need a special theorem that we will prove later. Okay, so we need to show that first, that Phi-X is actually an element of V star, the Phi as a map is linear, and norm preserving. Okay, so let's check first that Phi-X is a linear map. Lambda 2. No, let's not call it X. Let's call it lambda 1, lambda 2. So, but this is the map lambda 1, lambda. Oh, no, let's not call it lambda, too many lambda. Let's call it alpha 1, alpha 2, alpha 1 lambda 1 at x plus alpha 2 lambda 2 of x. And this is exactly alpha 1, the evaluation at x of lambda 1 plus alpha 2, evaluation of x plus lambda 2. Okay, so what we get is that phi x as a map from V star into R is linear. Let's check the continuity of this map. So phi x at a lambda, this is by definition, this is lambda x, and lambda is continuous, so this is less than norm of x, or norm of operator norm of lambda times operator norm of x, sorry, norm of x. But now let's not see this as a function of x, but as a function of lambda. So this is x is fixed, and now this tells us that the map as a map on lambda is bounded. And therefore, the operator norm of x in V star star is bounded by norm of x as a norm in V. So we proved that so phi x is in the double dual. Okay, now let's check that the map as a map in x is linear. So let's check that the map x in V goes to phi of x in V star star is linear. Okay, to do this, so we have phi of alpha x1, alpha 1 x1 plus alpha 2 x2 applied to some lambda. This is lambda of alpha 1 x1 plus alpha 2 x2, which now by linearity of lambda, this is alpha 1 lambda of x1 plus alpha 2 lambda of x2, which is equal to lambda 1 phi x1 of lambda plus alpha 2 phi of x2 lambda. So in other words, what we proved is that the map image of x1 alpha 1 plus alpha 2 x2 is the map alpha 1 phi of x1 plus alpha 2 phi of x2. So it is linear. Now let's check that this is an isometry. So is phi an isometric embedding? i.e., is the norm of phi at the image as an element in V star star equal as the norm of x in V? Okay, so this was already proved when we proved continuity. Now for the other inequality, we need a theorem about extensions of linear maps. This theorem is called the Hahn-Banach theorem. So what I will do now, I will use the theorem. I will tell you where, and then later we prove the theorem in a bigger generality. Okay, So we have to prove that the map is an isometry. We can fix an x. Of course, we can assume that x is 0 because 0 goes to 0. And now what we do, we have to create, we have to show the phi of x as norm equal to x. And for doing this, we have to evaluate phi of x at a good linear map. No? So we have to construct this linear map. So initially, what we do, we consider lambda be the linear map, not defined on all of V, but only on the vectors, on the line defined by x. So this map defined as lambda of alpha x equal to alpha norm of x. Okay, so this is obviously a continuous map, and but this is defined on a subset of V, because this subset of V. Now, by Hahn-Banach theorem, there exists an extension, maybe not unique, but an extension let's call it lambda tilde from V to R, continuous, I'll put in parentheses, an extension to extension for lambda. So what means is that if we take lambda tilde and we restrict it to Rx, this is equal to lambda. But moreover, this map has the same norm, with norm of lambda as an element of the dual of Vx, operator norm, is equal to the norm of lambda as an element in this vector, as the dual of this vector space here. Okay, but what is the norm of lambda? So this is the norm of lambda as Rx dual, but you see the norm of if you take alpha in such a way that alpha x is norm 1, then the value is exactly 1. So lambda has norm 1. Okay, so now therefore, how can we bound the operator norm of phi of x as a Bidual, as an operator on the Bidual? So this is at least the value of phi of x on the map lambda tilde we constructed, right? So divide by the norm of lambda tilde. But as we said, the norm, this map is, this norm is 1. This is the evaluation of phi tilde on x, which coincide with the evaluation of lambda. So the evaluation of lambda tilde on x, which coincide with the lambda on x, because this is an extension. So what we get, we get this is the evaluation of lambda on x, which is x. So we proved that the norm of phi of x is at least x. So since we already proved the upper bound, we proved that this is an isometric embedding. So we use this theorem by Hahn-Banach and about the extensions of linear maps. Now we are going to prove it. We're going to prove it in a slightly bigger generality. So let's say we have a vector space, and instead of having a norm, we can assume that we have just a semi-norm. So semi-norm, which means that P is linear respect to scalar multiplication of positive numbers for all and for all x in V. And 2 is sublinear. Px plus y is less than px plus py. This is for any y and for any x in V. Okay, a priori P could also be 0 for some non-zero vector. Now what we do, we consider a subspace. In our example before, this was a line. And we consider a map that is in the dual of W, right? And has a control. So lambda of x is bounded by this P of x. So in our case, this P was the linear map constant times norm of x for any x in W. Okay. Then the theorem says that there exists lambda tilde in V star. So now we define on all of V such that lambda tilde restricted to W coincide with lambda. And we have the same exact bound for all x in V. So this is the theorem. As a corollary, we have what we used before. So if you have a vector space or norm vector space, normed vector space, and we have a subspace, then for all lambda in W star, there exists lambda tilde in V star, such that lambda tilde restricted to W is lambda, and the norm of lambda tilde as an element of V star is equal to the norm of lambda as an element of W star. This is what we used before. So now let's prove the Hahn-Banach theorem. Proof. So the proof of the theorem of Hahn-Banach theorem. So for the finite dimensional case, it's very easy, but instead, in the case of the dimension of V infinite, relies on the axiom of choice. In particular, we shall use Zorn's lemma. Okay, so what we consider all possible extensions. So let's consider the set of all possible extensions of lambda. So what is this? This is it comes with pairs, so it's a subset or subspace and an extension. So where W tilde contains W, is a subspace of V, so subspace. Lambda tilde is an element of the dual of W tilde that extends lambda, and we have the bound on the norm W tilde of x is bounded by p of x. This is for all x in W tilde. Okay, so now on this set, we have partial orders. So an extension, two extension, if one extends the first one, we say that the second one is greater. And now, of course, if you have a chains of extensions, then this on the union of the subspace defines an extension. Okay, so this means that we can use, we are in the assumption of Zorn's lemma, and therefore we can consider maximal extensions. Let's call this maximal extension, may not be unique, W hat lambda hat. Now let's prove that this extension is actually extension for the whole space. So let's show that W hat is equal to V. Okay, so what we will do, we'll do it by contradiction, assuming that this is not the whole space, take an element in the difference and extend it to one more element, contradicting the maximality of this extension. So if not, we can take V, which is in V but not in W hat. If we extend to W hat plus this direct sum RV, we get a contradiction. Okay, so it's clear how we will define. We'll define it. So on W tilde, we already have the map. We have to just say what is the value on V, and then by linearity, all is forced. But one cannot choose arbitrarily the value on V, because we want to also preserve the same bound on the norm. Okay, so let alpha in R, this value to be determined. So we shall consider the map lambda tilde in W hat plus RV star defined as lambda tilde of W plus TV to be lambda tilde of W plus T alpha. So this is a hat. No, this is a tilde, and this one is a hat. T alpha. Okay. Clearly, this map is linear and continuous. Okay. We need to choose. We have to check the norm. So clearly, this phi tilde is in W hat plus RV star. We need to choose alpha to have the bound on the norm. Phi hat W plus T alpha less than P, the seminorm, evaluated at W plus TV. This is for all W in W hat and for all T in R. Okay, so now let's pay attention. So T could be positive and negative. Okay, so if t is positive, what we want is that lambda tilde of w divided by t plus alpha is less than 1 over t p w plus tv, i.e. we want that alpha is less than, put on the other side, so it's 1 over t minus lambda hat w plus p u plus tv, right? So alpha should be less on all of these numbers for all t positive, right? So it should be less than the infimum over all t. So if instead t is negative, so let's write t equal minus s with s positive. Now dividing by s, what we get is what we want is lambda hat w divided by s minus alpha less or equal than 1 over s p w plus minus s v for all s positive, i.e. alpha should be greater or equal than 1 over s alpha hat w minus p w minus sv for all s greater than 0, and therefore should be bigger than the supremum of all these numbers. So let me write that alpha needs to be chosen between all these values and all these values. Okay. So to be able to choose alpha, we need to show that the sup of all s positive and w in w of w hat w minus p w minus sv divided by s is less or equal to the infimum t positive and w in w of p w plus tv minus lambda hat of w divided by d. And then any alpha in between will work. Okay. So what we will do now, we'll take an arbitrary element of this. We will, one of these arbitrary t, we'll remove one of arbitrary s and show that this is a quantity that is always positive. Okay. So p w plus tv minus lambda hat w divided by t minus, now we will remove another arbitrary, but of course I cannot call it w anymore. I will call it w prime minus p w prime minus sv divided by s. We want to show, so the question, is this positive? Okay, so let's write it as, okay, put s and t in evidence. So I get, so s p w plus tv minus s lambda hat w minus lambda minus t lambda hat, there was a hat here, w prime plus t p w prime minus sv. Okay, now I use the linearity of lambda. So this goes inside, and the vector SW minus O plus TW goes inside. So what I'm saying is that all of this is equal to minus lambda hat SW plus TW prime. So and instead and then I use also the linearity of the semi-norm. So this one is equal to P SW plus STV. This one is equal to P TW prime minus STV. Okay, let's write it carefully. Now, so now this is really equal by linearity, equal 1 over ST P SW plus STV plus P TW prime minus STV minus lambda SW plus TW prime. Okay, so now what we have by the fact that we have a semi-norm, this object is less or equal than P of the sum, which is SW plus TW prime, because these two cancel. And now by the fact that the norm, that lambda is bounded by the semi-norm, we have that this quantity is greater than 0, because lambda is lambda hat is less than P. So this proves that there is room to choose some alpha. I will briefly discuss an example that we will discuss more deeply later. And the example is LP as with the P norm as a Banach space. This is not a norm space, but for P equal to 2, so this is not a Hilbert space, but for P equal to 2, this is a Hilbert space. And the scalar product between f and g is the integral of the function f times g. And as we saw for Hilbert space, then we can see that the map G goes to the integral of fg the mu. This defines an element in the Hilbert space L2 star, and therefore we have that L2 is isomorphic to L2 star. In case we have an arbitrary P, then what's possible is to consider another element called P star with the property that 1 over P plus 1 over P star is equal to 1. So there is only one P star defined by this relation. What happens is that if now G is in LP, then we can integrate G, which is multiplied by F, with F in LP star. And this function will be well defined and will define an element of the dual of LP. And therefore we will have this property that the dual of LP will be canonically isomorphic to LP star. We'll need to really understand that this is a well-defined map under this condition, but just to tell you that the duality, the self-duality of L2 has still some recollection in the case of arbitrary P. We will see that later in the course.